17.3 boundary effect reflections. So far, our discussion of wave, we have primarily considered wave traveling through a medium without interacting with any boundaries of the medium. Okay, so we now address the detail of the interaction of wave with the boundaries. Okay, for example, we're going to consider a pulse traveling to the right. String here, okay, is rigidly, okay, tied up to one end. When the pulse reaches the fixed end of the string, okay, the string produced an upward force on the support here. Okay, by Newton's third law, the support must exert an equal magnitude and oppositely directed downward reaction force on the string. This downward force, okay, causes a downward oriented reflected pulse, and then the reflected pulse going to travel in opposite direction. Now, if let's say we have a free end like this, okay, what will happen? Okay, this time the pulse arrive at the end of the string that is free to move vertically as in figure, right? The tension at the free end is maintained because the string is tied to a ring of negligible mass that is free to slide vertically on a smooth post without friction. Consider for perfect case firstly. Again, the pulse is reflected, but this time it is not inverted anymore. When it reaches the post, okay, the pulse exerts a force on the free end, okay, of the string, causing string to accelerate upward. Okay, the ring rises as high as the incoming pulse, okay, and then downward component of the tension force pull the string back, okay, down. This movement of the ring produce reflected pulse, okay, that is upward oriented. Finally, okay, we are going to consider a situation in which the boundary is intermediate between these two extremes, between the fixed end and also the free end. Okay, in this case, the medium does not end, but rather it changes in some way and continues. When, like this one, okay, when there is a change in the medium, part of the energy in the incident pulse is reflected and part undergoes transmission. Okay, part of it will be reflected, part of it will go transmission. That means some of the energy pass through the boundary. Okay, for instance, okay, suppose light string attached to heavier string. This is light string, this is heavier string, as this figure. When a pulse traveling on the light string reach the boundary, okay, between the two strings, okay, part of the pulse will be reflected back. Okay, and inverted, and part will be transmitted to heavier string. Okay, the reflected pulse here, this one, inverted for the same reason described earlier in the case of the string rigidly attached to a support or fixed end, we call it. The reflected pulse, okay, has a smaller value, okay, or amplitude than the incident pulse, based on conservation of energy here, because this is the incident or E initial. Okay, now after the incident, what will happen? It splits into two, right? So means that the energies, the sum of the energies of these two pulses, okay, the transmitted and the reflected, must equals to the energy of the incident pulse here, because the reflected pulse contains only part of the energy of the incident pulse. Its amplitude must be smaller. Now, okay, a pulse, incident pulse, is traveling on a heavy string, okay, strikes the boundary between the heavy string and the lighter one, as in this part, okay. Again, the same situation going to happen. Part of it going to be reflected and part of it going to be transmitted. Okay, in this case, the reflected pulse, okay, is not inverted in comparison to the previous diagram. In this section, okay, now we are going to combine the idea in 17.2 and 17.3. How do boundaries affect standing wave? Okay, in this figure, we have a string of L length, okay, fixed at both ends. Alright, so this is a similar model for a guitar string or piano string. Okay, wave can travel in both directions on the string due to the reflection from the both ends. Okay, so standing wave can be set up in string by continuous superposition of incident and reflected wave here. Right, so the boundary condition for wave on a string, because this is fixed end, okay, it must be zero displacement, so here should be node. Both of it must be node. Equation 17.2 will give us, okay, L equivalent to n lambda n over 2. Okay, where lambda here indicates that difference value of n will result in different value of the wavelength. The wavelength here, okay, determines the frequency of the wave according to the equation 16.12. Okay, the boundary condition results in the string having a number of discrete natural patterns of oscillation called normal modes. Okay, so the pattern called normal modes, each of which has characteristic frequency that is easily calculated. This situation in which only certain frequency of oscillation are allowed to call quantization. This is the one that I explained in early, the introduction of this topic. Quantization is common occurrence, okay, when waves are subject to boundary conditions, and is a central feature in our discussion of quantum physics in the extended version of these steps. The normal mode of the oscillation can be shown by this figure, right? Where we have in figure A here, okay, for the most basic or fundamental or order of 1, okay. This is the shape of this, the length of it is half of wavelength. So the L is equivalent to half of lambda 1, because this is the N1, so this is the first order. And for second pattern or second harmonic, we call it, okay, we have two loops here representing the standing wave, okay, and then the order is N equivalent to 2, and here lambda is equivalent to L. All the time the L is fixed from this point to this point, right? And for the third pattern or third harmonic, okay, you have 3 loops, right? The order is 3, okay, and the L is 3 over 2 lambda. This is one complete lambda here, one complete lambda, and this is half lambda. That is why it becomes 3 over 2 lambda. From here, we can see that, okay, lambda n is equivalent to 2L over n, where the n is 1, 2, 3, and so on, the integer. Okay, this is the harmonics, the order of the harmonics. Okay, and we know that F also equivalent to V over lambda. So Fn equivalent to V over lambda n. And what is our lambda here, and V K over 2L, right? Where the N is the integer, and so on. Okay, and we know that V is equivalent to V itself, T over mu, right? So we have this kind of the same condition. So this is what we call it harmonic series. Okay, and all the time, okay, another one, F n always equivalent to n F1 fundamental frequency or harmonics. For guitar, different harmonics or different frequency is produced by shorten the length of the string of the guitar by compressing the fret here. Example 17.3. Give me a C note. The middle C string on a piano has a fundamental frequency of 262 Hz, and the string for the first A above middle C, okay, has a fundamental frequency of 440 Hz. Calculate the frequencies of the next two harmonics of the C string. Okay, so you have given to you 440 and 262 is the fundamental frequency. The middle C on a piano, frequency of 262, right? So the frequency of the next two harmonics of the C string by make use of F2 equivalent to 2F1 equivalent to 5 to 4 Hz, and F3 equivalent to 3F1 equivalent to 786. If the A and C string have the same linear mass density mu and length L, determine the ratio of the tension in the two strings. Okay, so this equation is for F1A for string A, and then this is an equation for F1C for string C. If it has the same L and the same mu, we can have a simplified version by taking ratio between them. F1A ratio to F1C must equivalent to, right? Okay, 1 over 2L square root TA over mu over 1 over 2L square root TC over mu. So if you see here, you can cancel out this one and then also this part. Okay, so you are only left with square root TA over TC. Okay, so rearrange the equation, you will figure out the answer is 2.82. In other words, F1A equivalent to 2.82 F1C. If you look inside your real piano, you will see that the assumption made in part B is only partially true. The strings are not likely to have the same length. The string densities for the given notes might be equal. Okay, but suppose the length of a A string is only 64% of the length of C string. What is the ratio of their tension? Again, you are going to do the ratio of F1A to F1C, but then given that, okay, percentage, length of A string is only 64% of the length of the C. So you cannot simply cancel out 1 over 2L just now. Okay, then you're going to have like this. Okay, and then rearrange the equation because we want to know the ratio of the tension. So this is our interest. You will have this arrangement. Substitute 64 over 100, which gives you 0.64. Okay, and then you will get 1.16. Subtopic 17.5, resonance. Okay, so as of now, we have seen the system such a taut string, stretch string, is capable of oscillating in one or more normal mode, okay, of oscillations, okay, as we learned before, right? Okay, we find that if a periodic force is applied to such system, okay, the amplitude of the resulting motion of the taut strings, okay, will be greatest when the frequency of the applied, let's say coming from the vibrator here, is equals to one of the natural frequencies of the system that we have. This phenomenon known as resonance, okay, where we had discussed is in section 15.7 with regard to a simple harmonic oscillator, okay. Because an oscillating system exhibits a large amplitude when driven at any of its natural frequency, okay, these frequencies also known as resonant frequencies. Okay, so let's consider this figure now. This is figure 17.16 on page 465 from your textbook, okay. Where we have a string being driven by a vibrating blade, the source of the vibration or wave. When the frequency of the blade equals to one of the natural frequency of this string, okay, what will happen? Okay, standing wave are produced and the string going to oscillate, okay, with a large amplitude. In this resonant case, right, the wave generated by the oscillating blade here is in phase with the reflected wave, okay, and the string absorb energy from the blade. If the string is driven at a frequency that is not one of natural frequency of the string, okay, the oscillation are of low amplitude and exhibit no stable pattern. So if you be able to watch or observe a stable pattern like this, it means that the natural frequency of this string is reached by the vibrating blade system here. Alright. So examples of standing wave in air column right now, subtopic 17.6, standing wave in air columns. So we have lots of types of instruments that are using air as the medium of the wave, okay. The wave under the boundary condition model can be applied to sound wave in a column of air such that inside an organ pipe, right, or clarinet, okay, standing wave in this case are the result of interference between longitudinal sound wave traveling in opposite direction. So due to the combination of the reflected wave and the original wave, we have a standing wave produced within the air column or the instrument. Okay, in a pipe closed at one end, for example this one, right, the closed end has no displacement, okay. We call this point as node, okay, because the rigid barrier here, okay, at this end does not allow longitudinal motion of the air, right, because the pressure wave is 90 degree out of phase with the displacement wave. See, please refer to section 16.6. The closed end of air column correspond to a pressure antinode, okay. So it's opposite. The displacement is going to be displacement node, but for pressure is going to be pressure antinode. That is point of maximum pressure variation. The open end of the air column here is approximately a displacement antinode, okay, and a pressure node. We can understand why no pressure variation occurs at an open end by noting that the end of the air column here is open to the atmosphere outside. Okay, therefore, the pressure at this end must remain constant at atmospheric pressure. This is figure 17.17. Okay, for a pipe open at both ends. So if you take a look on this pattern, okay, the very fundamental or first or basic or fundamental harmonic or wave pattern produced within this air column when you have open at both ends, okay, in this pattern, which is, okay, this is, okay, 1/4 lambda, and here is another 1/4 lambda. 1/4 plus 1/4 is equivalent to half lambda, right? So in terms of physical diagram, we are going to have here, okay, as the antinode in terms of pressure wave, okay, and then here is node, okay, where we know that it is in opposite to the displacement wave, right? So for the first harmonic here, lambda 1 equivalent to 2L, right? And for the second pattern, okay, we call it second harmonic, okay, or mode, okay. What we're going to have here is antinode in terms of displacement wave, followed by node. In opposite, okay, for pressure wave, we have here node and antinode, and so on. So lambda 2 here, okay, we have 1/4, and this one is half, and 1/4. So 1/4, 1/4, you have half, here you have half, which is 1 complete lambda, right? And next one, okay, the third harmonic, okay, the third pattern that going to be produced within the air column, okay, is this one. You have 1/4, half wavelength, and 1/4 wavelength. So total up will be 1 and half. That is why you have 3/2 lambda L equivalent to lambda 3. And all the time, Fn is equivalent to NF1, right? And from this pattern, okay, we may produce or deduce a general equation of Fn equivalent to Nv/2L, where the n is the integer due to this, okay, repeated part here. We can observe that, okay, this formula actually almost the same to the formula where we have a taut string or stretch string. Fn equivalent to Nv/2L with n is 1, 2, 3 and so on, integer, for pipe open at both ends. We have another type of pipe, which is a pipe closed at one end. If it is closed at one end, the fixed end here, okay, in terms of displacement, going to be node. No displacement wave allowed here. In terms of pressure wave, it's going to be antinode, because this should be maximum pressure wave. Okay, at the open end here, for the displacement wave, is going to be antinode. Okay, but for pressure wave, it's going to be opposite, which is node for pressure wave, right? So if we observe the shape or the pattern of the harmonic produced, the fundamental of first harmonic produced here is equivalent to 1/4 lambda. So for this pattern, L, the total length of the air column, is equivalent to 1/4 lambda 1. Okay, so from here, we may rewrite it, lambda 1 equivalent to 4L. From V equivalent to lambda F, okay, we may now rewrite for F as our interest is equivalent to V over lambda, right? So our F here, okay, V F1 here, V over lambda 1, which is V over 4L. For the rest of the F, okay, we may deduce the same method by using the same technique. We may deduce the formula for F, the following F of frequencies, okay, where in general the frequencies is equivalent to this. Fm equivalent to mv over 4L, where the m is equivalent to odd orders 1, 3, 5, 7, and so on. Okay, and if we want to make it in terms of integer orders, okay, you may also use this method, Fn equivalent to 2n minus 1 v over 4L, where n equivalent to integer. But madam suggests for you to use only this one. Is enough. Provided that you memorize, you must remember that the m must be odd order. Then next one, we always know that Fn is equivalent to n F1. Okay, still valid and applicable for this pipe close at one end. Alright, but then again, okay, it must be odd orders. So means that for pipe close at one end, for example this one, right, we only can have odd patterns, okay, odd harmonics. So we have first harmonic, third harmonic, and fifth harmonic. We don't have second harmonic, fourth harmonic, sixth harmonic, and so on. So we only have odd harmonics. Okay, so in general, equation for pipe close at one end, Fm equivalent to mv over 4L, where m is odd orders. So standing wave in air column, we have lots of instruments that use standing wave in air column. Example 17.5, wind in a culvert. A section of drainage culvert 1.23 meter in length makes a howling noise when the wind blows across its open ends. Okay, determine the frequency of the first three harmonics of the culvert if it is cylindrical in shape and open at both ends. Takes V equivalent to 343 meter per second as the speed of sound in air. Okay, so since this is open at both ends, so we have a general formula of N equivalent to NV over 2L, where your N is integer. Right, so for the first one, F1, okay, N is equivalent to 1 times with the V, speed of sound in air, okay, over 2L. So you have, this is your fundamental frequency. So for F2, second harmonic, you may directly use the shortcut of 2F1, or if you want to put it in terms of details, F2, okay, equivalent to 2 times V over 2L. So V over L, right? So it will give you same amount to this. Okay, for F3, okay, again, you may directly use the propagation formula like this, F3 equivalent to 3F1, alright, which give you 418, or you again may calculate it in detail like this. You will get the same answer. Okay, with this. Alright. Example 17.6, measuring the frequency of a tuning fork. Okay, a simple apparatus. for demonstrating resonance in air column is depicted in the figure here. Right. A vertical pipe open at both ends, okay, is partially submerged in water, and tuning fork vibrating at an unknown frequency is placed near to the top of the pipe. Right. The length of the L of the air column can be adjusted by moving the pipe vertically. Okay. The sound wave generated by the fork are reinforced when L corresponds to one of the resonant frequency of the pipe. For a certain pipe, the smallest value of L for which a peak occurs in the sound intensity is 9 cm. Right. So as we know, for this pattern, we are going to have close at one end. Okay, open pipe, close at one end. Right. So here going to be antinode for pressure, which is node for displacement wave. Okay, so for open at one end pipe, so the total length here is equivalent to lambda over 4 because of the shape here. Right. For this one, second harmonic, or we call it second resonant or third harmonic. Okay, you have 3 lambda over 4 is equivalent to total length. And for the third resonant or fifth harmonic, okay, we have total length here equivalent to 5 lambda over 4. A. What is the frequency of the tuning fork? So since this is a formula, this is a case of close one end. So for the basic or fundamental frequency or the first harmonic, the n is equivalent to 1. So you have 343 over 4 times 0.09, which give you 953 Hertz. B. What are the values of L for the next two resonant conditions? Okay, by make use of lambda is equivalent to V over F. This is actually coming from V equivalent to lambda F, right? So you are going to determine the lambda firstly. Okay, V over F equivalent to your lambda, so it's equivalent to 0.36 Hertz. Okay, based on this figure, if you refer to this, okay, and this, for the second resonance or third harmonic, okay, the total length here is equivalent to 3 lambda over 4. So you may calculate the total length of it, which is 3 over 4 lambda. Okay, so make use of this lambda, substitute it here. You will have the L is 0.27 for the second resonant or third harmonic. For the third resonant or fifth harmonic, okay, so the L is equivalent to 5 lambda over 4. So substitute the value of lambda here. You will get the L for the third resonant or fifth harmonic, which is 0.45 meter. 17.7 beats, okay. Specifically is about interference in time. Okay. If you refer to this statement, beating is the periodic variation in amplitude at a given point due to the superposition of two waves having slightly different frequencies. This is the meaning of beats. So why is it happened? Okay. So the interference phenomenon we have studied so far involve the superposition of two or more waves having the same frequency, if you still remember. Because the amplitude of the oscillation of elements of the medium varies with the position in space of the element in such a wave, we refer to the phenomenon of spatial interference. Okay, standing wave in strings and pipes are common example of spatial interference. Okay, now let's consider another type of interference, one that results from the superposition of two waves having slightly different, the keyword slightly different frequencies. Okay, in this case, when the two waves are observed at a point in space, they are predictably in and out of phase. That is, there is a temporal, or we call it time in simple, alternation between constructive and destructive interference. Okay. As a consequence of it, okay, we refer this phenomenon as interference in time. We can also call it as temporal interference. So how we are going to combine the two waves, okay, can be shown by following equation. Right. So if let's say you have, this is your y1, right, is equivalent to this. So this one also equivalent to this. So remember, between sin and cos we can interchange, okay. So which is the difference is only 5/2, right. So omega itself is 2 pi f, right. So and y2 is this amount. It's just that they are different in terms of, slightly different in terms of frequency or angular frequency, or f1 and f2. So if we have beating process, it means that interference in terms of time interval, or we call it temporal interference, going to happen. So interference means that they're going to combine, okay, based on superposition principle. So the product of these two combined is equivalent to this, right. So this is in this figure, okay, we can see that, let's say y1 is the green wave, right, and then y2 is the blue wave. So there is some instant, okay, they meet at the same point, okay, and the same instant, some of the time they almost meet at the crest, okay, and sometimes they meet at the throw, but then sometimes they are in almost in opposite, you see. So that is why we call it temporal interference, okay, or interference in time. But not to worry too much on this equation, okay, we are going to focus more on the product of it only, not on how to derive of it. So this is the step on how to get the solution for this process. So not to worry, to solve this one, okay, trigonometric identity must be used. But again, as I stated just now, not to worry too much on the derivation part. Okay, finally, you will get this as your solution for cos 25 plus minus 1. Okay, so the one that important to you is FB is equivalent to modulus of F1 minus F2. Therefore, the one that you're going to memorize or important for you is this one, not the whole process of deriving. Okay, please memorize this one. So in terms of a wave, okay, so what beats look like, okay, this is the beat, okay, it is within an envelope, okay, combination between the green wave and the blue wave produce the brown wave here. Say the moment it reach, okay, at this point is almost maximum amplitude of this wave, okay, here, okay, but then at this point here, completely out of the phase. That's why for the resultant wave, it is on the y equivalent to 0, right, and here 0 again, and here almost maximum, and here 0 again. So this is the beat, okay, and the frequency of this beat is this one. Example 17.7, the mistuned piano strings, two identical piano strings of length 0.75 meter are each tuned exactly to 440 Hz. The tension in one of the string is then increased by 1%. If they are now struck, what is the beat frequency between the fundamentals of the two strings? Okay, the solution. Okay, we are going to do the ratio between F2 and F1. So F2 is V2 over 2L and F1 is V1 over 2L. So since the length of the string is the same, so we can cancel out the 2L. So we are left with V2 over V1. So what is V for piano? Is a stretch string or taut string. So V is equivalent to square root T over mu. Okay, for V2 it's T2 over mu, and for V1 it's T1 over mu. So mu is the same thing, same character, because it's identical string. Right, again, cancel out each other. So we are left with square root of T2 over T1. And it is informed to us just now, okay, T2 is equivalent to 1.01 of T1. Okay, this is the information coming from this. Okay, it's increased by 1%. So that is why you have 1.01. Okay, this is about 100%. This is the 1% just now. Alright, and then substituting T2, okay, equivalent to 1.01 T1 over T1, cancel out the T1, then you are left with that, which equivalent to 1.005. So from here, okay, we may notice now F2 is equivalent to 1.005 of F1. So what is F1? F1 here is 440 Hertz. That gives us the answer for it. For F2 is 442 Hertz. Are we done? Not yet, because the question asking for beat. So beat is actually modulus of F1 minus F2. So it's regardless whether F2 minus F1 also can be done. So the frequency of the beat is 2 Hertz.